Chapter 1. Prologue. It is commonly assumed that the everyday world we live in is material. If we walk down the street, the ground beneath us will still be there after we have left. If we kick a stone, it will feel real and solid. However, is this really the case? Is it possible our intuitions are misleading us? According to an emerging consensus among theoretical physicists, the surprising answer is yes. In the search for a theory of quantum gravity unifying quantum mechanics with Einstein's theory of general relativity, the astonishing discovery has been made that the physical universe is not fundamental. Rather, according to quantum gravity experts, not only matter, but the very fabric of spacetime itself is generated by quantum information existing outside of physical reality. Chapter 2. Virtual Reality Physics. But if the world we see is generated by non-physical information, this raises the hair-raising question: do we live in a virtual reality? The parallels between computer science and theoretical physics has not escaped the notice of many physicists working in the field.
The universe is effectively a quantum computer. In fact, not even effectively, actually is a quantum computer.
The future, at least of this development, will be that we start actually with information. So information is going to be our starting point. And space-time is not something that we start with.
Space-time is not fundamental. The space-time is, if you like, an effective emergent description from something else that underlies it. And that something else could be information in the following way.
So underneath the molecules and atoms and particles, there's another layer of reality that's coming to light. It's a layer that's based on information.
To investigate this, computer scientist Brian Whitworth compared the weirdnesses in modern physics to both the expected behavior of particles in empty space in an objectively real world, and to the behavior one would expect out of information processing in a virtual reality. After mapping out the parallels, it was astonishingly found that the weirdnesses of modern physics fit the predictions of a virtual reality better than those of a real world. Meaning, our world behaves more like the inside of a computer game than a world made of material atoms in an empty void. Some of the numerous examples Whitworth investigated include pixelated spacetime. Everything within a virtual reality is broken down into pixels with minimum sizes. If the world were real, however, we would expect there to be no smallest size. One could simply go smaller and smaller. However, as it turns out, the physical universe is pixelated. Even space and time have smallest sizes and durations called the Planck length and Planck time, respectively.
Space at the Planck length resembles the grid on a football field. The yard lines are the fabric of our universe, and there's simply nothing in between.
It could be that time jumps from one discrete point to another, and there are no steps in between.
Like little quantum mechanical ants could tunnel from one spot on the grid to another spot on the grid without ever going into the intervening space in between. Why? Because there isn't any intervening space in between.
Sizes smaller than 1.6 times 10 to the negative 35 meters and time smaller than 5.4 times 10 to the negative 44 seconds do not exist in our universe.
There is one surefire way to tell if you're looking at a computer simulation. Zoom in. Every computer-generated image, no matter how realistic, breaks down into pixels when you get close enough. You might think this doesn't happen in the real world, but you'd be wrong. In the past century, physicists have discovered that matter really is made of tiny little pixels, fundamental, indivisible particles billions of times smaller than an atom. The theory that explains all this, quantum mechanics, applies not just to matter, but to the entire universe.
Look at the way the universe behaves. It's quantized. It's made of pixels. It's made of individual atoms. Space is quantized. Time is quantized. Energy is quantized. Everything is made of individual pixels.
A maximum speed limit. Our real-world intuitions tell us that velocity can increase without limit, since there should be nothing to stop it. However, with the advent of Einstein's theory of special relativity in 1905, it was discovered that this is not the case. According to relativity, nothing can go faster than the speed of light. Curiously, this exactly parallels the behavior of virtual realities. Virtual realities, such as computer games, are the product of information processing, and information processes at a certain speed. As a result, a computer game will have a maximum velocity determined by its refresh rate, exactly as seen in the real world. Objects only render upon observation. Naively, we expect objects to exist when we are not looking at them. However, on close investigation of the quantum world, we discover that this intuition is actually wrong.
So there's also the Einstein-Podolsky-Rosen paper, which puts forward that quantum mechanics implies either the non-existence of objective reality or the non-existence of locality. Can you say something about that? And would you say that's still a valid interpretation?
The point is, there's not only Bell theorem, there's another theorem which is called Koch and Specker theorem. It's much less known. And that theorem tells us that the culprit is actually our notion of reality. Because the Koch and Specker theorem talks about properties of one system only. So we know that we cannot assume, to put it precisely, we know that it is wrong to assume that the features of a system which we observe in the measurement exist prior to the measurement.
In the quantum world, particles are not actually there before we look, but rather exist in a blur of possible states. When we look, the particle takes on one of these states. And though quantum weirdness blurs out at larger scales, it never actually goes away. The view that the quantum and classical worlds are somehow separate, called macrorealism, was falsified by tests of the Leggett-Garg inequality in 2011. The only difference between the two is in our minds.
No, no different. Only different in your mind. You must unlearn what you have learned.
But couldn't one say that this involvement of the observer is really just limited to very small quantum mechanical systems, and once we come to the real world, surely all quantum effects would have just gone?
As people say that, and this is a comforting possibility, but there's no reason to believe that. Nothing in the theory tells us that. There's no limit for the validity of quantum mechanics, and we and other groups are actually exploring how far can you go, and I'm sure that we will go to sizes which will be quite surprising. So in my eyes, this is just temporary. In the future we will realize quantum phenomena for sufficiently large objects such that it's obvious that quantum mechanics cannot be limited to small particles, and then the philosophical implications become more relevant because people cannot put them into some corner.
However, this parallels exactly how video games behave. In a video game, objects only exist when they are rendered by an observer. Before that, they are just data on a hard drive.
These basic rules of quantum mechanics apply to all tiny subatomic particles. When we look at them, they are just dots. When we look away, they lose their physical form.
A different way of looking at that is to say, well, how parallel is this behavior with what I see in my PlayStation 3 when I'm playing a video game? In a PlayStation 3, an example of that is SimCity. It's an enormous city. I can navigate my way through every bit of it because the PlayStation, the video game, gives me the frame that I need when I'm looking there. If I look somewhere else, it'll create that frame. Well, oddly enough, the universe behaves that way in reality. The universe gives you what you're looking at when you're looking at it. When you're not looking at it, it's not necessarily there.
Our world is pixelated and only assumes definite form when observed, the very same way our computer simulations behave.
A cosmic beginning. This one is something of a giveaway. The fact that the physical universe came into being at the Big Bang demonstrates that it is not actually fundamental as we would expect if it were real. Rather, it had to come into being from something more fundamental. This exactly parallels the startup of a virtual reality. Once a computer game is created, such a Big Bang occurs, and a whole virtual reality comes into being.
If all of this is some kind of informational process running in some machine, the machine is not in this universe. It's somewhere else, and this universe is a consequence of its running. And so that's just a bizarre kind of fact, but it solves one very difficult problem, the cosmogony problem, which is how did the universe get started? And I've never seen anything more harebrained than the ideas that came up with the Big Bang starting as some kind of quantum mechanical, just nothing turning into something. This doesn't have to be a mystery that goes on and on and on, because if there is a computer running things, the place where the computer is doesn't have to have the same laws we have.
I see.
They don't need to be a kind of place that has beginnings and endings.
Whenever we talk about reality, even think about reality, we really handle information. The two are not separable. So maybe now this is speculative here, maybe the two are the same, or maybe even information is constitutive to the universe. And this reminds me of the beginning of the Bible of St. John, which starts with, "In the beginning was the Word."
Non-locality. In an objective reality, particles influence each other by interacting with each other in nearby space. However, in a virtual reality, interactions can occur between objects in two separated regions of space, as all points in a virtual reality are equidistant to the source of their simulation in the hard drive. As it turns out, just such a phenomenon exists in the real world. Quantum entanglement links two seemingly separate particles across vast distances, such that a change to one instantly determines the state of the other.
The key to making these miracles come true is a process called quantum entanglement, and scientists are already harnessing this astounding discovery for both civilian and military purposes.
In quantum physics, what happens to an object over here can instantly affect an object over here, and over here could be millions of miles away.
This is how it works. When two subatomic particles interact, they can become entangled. That means their spin, position, or other properties become linked through a process unknown to modern science.
If you then make a measurement of one of the particles, then that instantaneously determines what the behavior of the other particle should be. And when the experiment is done, it's found that indeed the other particle's quantum state is exactly determined once you've made a measurement of the partner particle's quantum state.
That means if a scientist observes one entangled particle and forces it to spin clockwise, the other entangled particle will immediately start spinning in the opposite direction. That seems intriguing, but it's hardly earth-shattering until you consider that the two entangled particles can be separated by billions of light years. And still, the moment you observe one particle's spin, you've dictated the other particle's spin.
You can treat some of these particles as having two possible outcomes of a measurement. And you can think of that as heads or tails of a coin. So you create two of them, you give one to your friend goes off somewhere and you keep the other, and you both flip the coin. And if you come up with heads, they come up with heads. You come up with tails, they come up with tails. Heads, tails, it just goes back and forth, and yet they're the same answer on both sides. And again, there's no mechanism, there's no reason they would be. The scientists have gone through the different possible tricks. Like, for instance, are they double-sided coins? Are they trick coins? And they've kind of done experiments to rule that out. Is there some kind of surreptitious radio signal passing between them? They've ruled that out. Is there some kind of predetermination? I mean, they've gone through all the options, and yet they can't explain why these coins land on the same side. But now I think the progress of science and of understanding of the nature of space and time have taken us to a possible explanation. So if you think of those two coins, they're on opposite sides of the universe or their continent or wherever they may be, but they act as though they're right next to one another. They act as though they're kind of nuzzled up together. So they don't seem to have any distance between them. They're acting as though there's no distance between them, although you go measure the distance, it's enormous. So the proposition is that the distance between them is somehow an illusion. It's somehow a kind of a mirage. Or maybe a better way of putting it, it's a construction. That those particles or those coins in the metaphor are rooted in a layer of reality where the distance doesn't seem to exist. They're juxtaposed, even they look like they're far apart. And the distance is real to us, so it's real at our level of reality, but it's not real to the particles.
Particles that are identical in all respects. In a virtual reality, every object created by the same program is identical in all respects. The same is true for subatomic particles. Classes of fundamental particles have very precise properties that are alike in all respects as though they were copied from the same program. Time slowing near massive programs. Anyone who has opened too many windows at once in their desktop can readily recognize the similarity. Too many programs, or too large a program, will eat up the computer's processing power, and the computer will begin to slow down. Interestingly enough, just such an effect exists in modern physics. According to general relativity, the more you concentrate mass or energy into a region of space, the more time slows down.
With general relativity, we learn that the gravitational force is best described in terms of warps and curves in space and time. And that's most directly evident at the edge of a black hole where gravity is strong and the warpage of space and time is strong. And the way we see that is, if you were to go to the edge of a black hole, but have, say, strong rocket engines so you don't fall over the event horizon, so that you can actually, say, stay in orbit around the edge of a black hole, time for you would slow down compared to the rate of passage of time of somebody far away. So, for instance, you might stay around the edge of a black hole for a week. But when you come back, say, to Earth, you might find that 10 years have gone by.
This is not merely a coincidence either. In 1995, Ted Jacobson of the University of Maryland demonstrated that the warpage of spacetime in general relativity can be explained in terms of the density of information in a given region of space. According to his theorem, the more information is packed into a region of space, the more time will slow down in that region. Empty space which isn't actually empty. In a materialistic universe, empty space is, well, empty. When the ancient Greek materialist Democritus spoke of atoms and the void, he conceived of the void to be empty nothingness. However, modern physics tells us this is not the case. The Heisenberg uncertainty principle requires the existence of a zero-point field, or ZPF, everywhere, even in a perfect vacuum. If one thinks of a virtual reality, however, this makes sense. In a VR, empty space is not actually empty space, but is rather a simulation of empty space. The emptiness of space would then be generated by information processing. Instead of being truly empty, it would display information processing effects and contemporarily spawn objects, much like the virtual particles in the ZPF. Creates back histories. In computer games, what you don't observe isn't there. But when you look, the computer renders objects in place as though they had been there all along. And if these objects were programmed to be moving beforehand, the computer would generate an artificial back history for the object. Curiously, exactly such an effect is seen in quantum eraser experiments. The past history of an unobserved particle can be determined in the present, seemingly altering what happened in the past by how the experimenter chose to observe the particle.
This is like a high-tech version of the double hole experiment. Electrons are being fired toward a barrier with two holes in it. But the scientists can delay their decision about whether to observe the electrons until after they've passed through the holes, but before they hit the screen. It's as though I'm on a baseball field, and there's a baseball being pitched toward the barrier with the holes in it. But my eyes are closed, so it goes through, and it behaves like a wave, but then, at the last second before it hits the screen, I open my eyes and decide to observe it.
At that moment, the electrons, in essence, become particles, and seemingly always were particles from the time they left the electron gun.
So it's as though they went back in time to before they went through the holes and decided to go through one or the other, not through both as they would have had they been behaving like waves. That's really crazy.
That's the enigma. That our choice of what experiment to do determines the prior state of the electron. Somehow or other, we've had an influence on it which appears to travel backwards in time.
Processing limitations per area. Due to load processing limitations, virtual environments can only process so much in a given area. Meaning, if one thing is being simulated to an arbitrary level of precision, something else cannot be. Coincidentally, this is exactly what is seen in the Heisenberg uncertainty principle, which shows that pairs of properties such as location and momentum cannot coexist with arbitrary precision. If the location is fully rendered, the momentum cannot be, and vice versa. Tunneling effects. Alongside the uncertainty principle, load processing limitations lead to another curious effect seen in quantum mechanics referred to as quantum tunneling. In the quantum realm, objects will sometimes pass through barriers and appear on the other side. The higher energy or mass they have, the more likely they are prone to do this. Interestingly, this exact same phenomenon is seen in computer games such as Minecraft or Second Life. The reason? The computer is unable to process the barrier and the object tunneling through it at the same time. The larger the program of the object, the more likely it is to pass through the barrier. For instance, on Minecraft, the higher energy cows have a better chance of quantum tunneling through the fence than the lower energy chickens.
Basically, if you leave a marble in a cup in Second Life, and you leave all night, and you come back, what happens? The marble's gone. And it actually turns out that that problem isn't fixable. If you don't want that little marble to leave the cup that it's in, you actually would have to have an infinite amount of computing power to guarantee that it won't over a certain amount of time. Does everybody sort of see where I'm going with this? So what was just incredibly interesting to me, and I was already very interested in virtual worlds, was this bizarre fact that the computational limits imposed by simulation when you were simulating a virtual world on a computer essentially resulted in the same kind of, I'm just going to say, artifacts or problems that make quantum mechanics weird.
Space that emerges from non-space. Perhaps the most astonishing discovery of modern physics is that the fabric of spacetime is emergent from something beneath it.
What we're seeing is that the whole notion of space and time is probably not really fundamental. So space...
That sounds incredible, that space and time is not fundamental.
So the idea is that the concept of space, of distance, all the spatial concepts we deal with in science are emerging from that deeper level. They're not fundamental in the world. They're derivative.
In the quest to find the elusive theory of quantum gravity, the attempt to merge quantum mechanics and general relativity, researchers have discovered that spacetime is not actually fundamental, but emerges from information. Despite competing models of quantum gravity, the one thing researchers have reached consensus on is that whatever the ultimate theory is, it will have emergent spacetime. This is of course no different than the space in a computer game emerging from the information in the hard drive.
The future, at least of this development, will be that we start actually with information. So information is going to be our starting point. And space-time is not something that we start with.
Contains actual computer code. And if all of this were not enough, in 2008, Presidential Science Advisor and John S. Toll Professor of Physics at the University of Maryland, James Gates Jr., found computer code embedded within the equations of superstring theory.
These are pictures of equations. I've been, for the last 15 years, trying to answer the kinds of questions that my colleagues here have been raising. And what I've come to understand is that there are these incredible pictures that contain all the information of a set of equations that are related to string theory. And it's even more bizarre than that, because when you then try to understand these pictures, you find out that buried in them are computer codes just like the type that you find in a browser when you go surf the web. And so I'm left with the puzzle of trying to figure out whether I live in the matrix or not.
Wait, you're blowing my mind at this moment. So you're saying, are you saying your attempt to understand the fundamental operations of nature leads you to a set of equations that are indistinguishable from the equations that drive search engines and browsers on our computers?
That is correct. So
wait, I have to just be silent for a minute here. So you're saying as you dig deeper, you find computer code writ in the fabric of the cosmos?
Into the equations that we want to use to describe the cosmos, yes.
Computer code?
Computer code, strings of bits of ones and zeros.
It's not just sort of resembles computer code, you're saying it is computer code.
It's not even just is computer code, it's a special kind of computer code that was invented by a scientist named Claude Shannon in the 1940s. That's what we find very, very deeply inside the equations that occur in string theory and in general in systems that we can say are supersymmetric.
So are you saying we are all just, there's some entity that programmed the universe and we're just expressions of their code?
Well, I didn't say that. Some of those
like the Matrix? That's what you said.
Some of those codes are showing on the screen behind you right now. They don't look like codes, but these pictures, which we call adinkras, are graphical representations of sets of equations that are based on codes. So this is, in fact, to answer your question more directly, I have in my life come to a very strange place because I never expected that the movie The Matrix might be an accurate representation of the place in which I live.
If one is really in the Matrix, how better a way to tell?
So by studying the equations that, that I've been knocking around with forever, in the last 5 or so years, I've been able to show that hidden inside of these equations, there are computer codes. They're the kind of computer codes that make browsers work. And so if the equations that describe our reality have computer codes hidden in them, that's just kind of weird. And in fact, it's so weird that I like to tell people, let's go back to the Matrix movie. If there were physicists in the movie and they want to know they were inside the Matrix, how could they do that? Well, one way might be to try to detect computer codes in the equations that describe their world. But that's what I've just proposed.
Given the small sampling of parallels Whitworth investigated, the evidence very strongly supports the theory that we are in a virtual reality. As Brian Whitworth says, individually, none of the above short points is convincing, but taken together they constitute what a court might call circumstantial evidence, favoring virtual reality against objective reality. When coincidences mount up, they present a plausibility argument, if not a proof. More powerful evidence is provided by cases which a virtual reality theory explains easily, but which objective reality approaches have great difficulty with. Chapter 3. The Falsification of Realism. The evidence is overwhelming, but is there any way to actually know for sure? To put the virtual reality theory to the test, we will need an experiment to test whether realism is true or not. In 2007, just such an experiment was conducted by a team of researchers led by Anton Zollinger and Markus Aspelmeier in Vienna, Austria. The experiment tested a mathematical proof called Leggett's inequality, which described the behavior of quantum systems, if non-local realism were true. Given that local realism had already been falsified in 1982, the experiment was a test on realism itself as well.
What does that mean?
It means buckle your seatbelt, Dorothy, because Kansas is going bye-bye.
Astonishingly, once the experiment was performed, Leggett's inequality was violated, falsifying realism in the process.
So recent experiments led by the group at the University of Vienna, Austria, provide the most compelling evidence yet that there is no objective reality beyond what we observe. So it's really the observation that creates the reality. And what they found is that Leggett's inequality is violated as well as Bell's. Even if you allow for instantaneous influences, quantum measurements do not fit with the idea of an objective reality. So as they say in the magazine, rather than passively observing it, we in fact create reality. Now, if quantum theory denies the straightforward physical reality of atoms, it would also seem to deny the straightforward physical reality of chairs, which are made of atoms. Now, we like to think that the world can be divided into quantum and classical realms, and in fact, that's sort of the way physics operates practically. But in fact, there really is, only one reality here, and the transition from quantum to macro reality is not a real one. In fact, it's not even really blurry. There's one continuous law of physics that takes us from one level to the other.
Do not try and bend the spoon. That's impossible. Instead, only try to realize the truth.
What truth?
There is no spoon.
There is no spoon?
This sent shockwaves through the physics community, with physics world even stating that the experiment meant that quantum physics says goodbye to reality. Realism was found to be false, and the virtual reality theory had been confirmed. We are not living in an objective reality after all.
Who deserves to trust their intuition more than Einstein? And Einstein's intuition told him, like everybody's intuition tells them, that things are really there when you're not looking at them. Well, he was wrong, right? That intuition is incorrect. The universe is effectively a quantum computer. In fact, not even effectively, actually is a quantum computer.
But if we really are living in a simulation rather than an objective reality, then who is the simulator? Physicist Ed Fredkin defines the reality outside of the simulation as other. But what exactly is going on inside Fredkin's other remains mysterious.
The computer is somewhere else, someplace I call other, some other place. And the point is, if all of this is some kind of informational process running in some machine, the machine is not in this universe. It's somewhere else, and this universe is a consequence of its running. And so that's just a bizarre kind of fact. So there could be some place I call other, and in other, someone is either doing an experiment, something is doing an experiment, or an accident happened, a bug in the program, and that's this universe.
Chapter 4, Bostrom's Simulation Hypothesis. What is the explanation for the strange physics of our world? Are our brains plugged into a program like in the Matrix? Are we being simulated in a video game like on the 13th floor? The Oxford professor Nick Bostrom thinks he has the answer. According to Bostrom's simulation argument, it may actually be more probable that we are in one of many potential future simulations of the world, rather than in the one actual real world.
There is this article that I published back in 2003 presenting the simulation argument. This is an argument that tries to show that at least one of three propositions is true, although it doesn't tell us which of these three. The three propositions in question is first, that almost all civilizations at our stage of technological development go extinct before they reach technological maturity. So that's the first possibility. A second possibility is that there is a very strong convergence among all technologically mature civilizations, in that they all lose interest in creating ancestry simulations, as I call them. These would be very detailed computer simulations of people like their historical forebears, detailed enough that the simulated people in these simulations would be conscious. So the second possibility is that they just lose interest in doing this. And the third possibility is that we are almost certain of living in a simulation. So there's this argument that shows that one of these three is true. And the full argument involves some probability theory, but the basic idea can be grasped quite simply, which is that suppose it were the case that the first possibility did not obtain. So then some non-trivial fraction of civilizations at our stage eventually reach technological maturity. Then suppose the second possibility also does not obtain. So some non-negligible fraction of those mature civilizations are still interested in using the resources to running ancestry simulations. You can then show that because each mature civilization that devoted some resources to this purpose could run astronomical numbers of ancestry simulations, you can show that if the first two possibilities do not obtain, then there will be many, many more simulated people like us than there will be non-simulated people like us. In other words, almost all people with our kinds of experiences would be living inside simulations rather than outside them, if the first two possibilities are false. And conditional on that, we should therefore think we are probably one of the typical simulated people rather than one of the exceptional non-simulated people.
Is Bostrom's simulation argument an explanation for the physics? It might be, were it not for one small detail. The laws of a non-simulated world would not be the result of information processing, and thus would not display the hallmarks of a virtual reality such as in quantum mechanics and relativity. However, quantum mechanics allows for things to be in a superposition of possible states. When this principle is applied to computing, this gives us the concept of a qubit, a bit which instead of being either a 1 or a 0, is a superposition of many 1s and 0s at the same time. In our world, quantum computing is found everywhere, with qubits being found all over nature, from the photosynthesis in plants to the microtubules in your very brain. To simulate all of this in a classical computer, however, all of the qubits would have to be unpacked into classical bits, resulting in a hard drive larger than the universe. Since this would be absurd to posit and impossible to build, it follows that any world simulating our world with qubits must also have qubits itself, and therefore also obey the laws of quantum mechanics like our own. However, if it has laws like ours, then it must also be based on information processing. Thus, whether we are living in a future simulation or not, Bostrom's simulation argument curiously does not explain the physics. But if Bostrom's simulism is not the explanation for the physics, what is? Can we even know? Perhaps a closer look at the physics may help us here. Chapter 5. Entangled Spacetime. In the quest for the long-sought theory of quantum gravity, loop quantum gravity and string theory have both arrived at the holographic principle, the idea that our three-dimensional universe is in reality a hologram of information, stored in a two-dimensional horizon.
I seem real enough, don't I? Well, yes. But surprising new clues are emerging that everything, you and I and even space itself, may actually be a kind of hologram. That is, everything we see and experience, everything we call our familiar three-dimensional reality, may be a projection of information that's stored on a thin, distant, two-dimensional surface. Sort of the way the information for this hologram is stored on this thin piece of plastic.
Using the holographic principle as a tool to study the two-dimensional horizons of entangled black holes, Leonard Susskind and Juan Maldacena discovered what is known as the ER equals EPR correspondence in 2013. When the entangled horizons of two black holes are translated into 3D, their holographic images produce the two mouths of an Einstein-Rosen bridge, or wormhole.
The second way you can think of it is as a pair of black holes infinitely distant from each other, or you can say on two completely separate non-interacting sheets, two separate black holes in two completely non-interacting worlds where the two black holes are maximally entangled. Maximally entangled I take to mean this kind of state here. All right, so if you have two black holes in otherwise non-interacting world, in fact, not otherwise, in a completely non-interacting world, but you entangle them in this form here, the statement is that they form a Einstein-Rosen bridge between them.
However, if locations, such as those of the twin mouths of a wormhole, are defined by quantum entanglement, and in turn space is defined by locations, then space itself is defined by quantum entanglement. This realization gave rise to the ADS mirror correspondence a year later, which showed that spacetime geometries in general emerge from entanglement. But is there any way to test this? Quantum gravity is notoriously hard to test, and without an experiment to confirm it, the ADS mirror correspondence would remain in the realm of theoretical physics. So is there any way to know for sure? As it turns out, quantum mechanics may give us something of a shortcut here. The discovery of quantum non-realism in 2007 has implications not only for matter, but for space itself. According to quantum non-realism, the locations of particles do not exist prior to measurement. However, when entanglement is thrown into the mix, this produces a curious result. If the locations of two entangled particles do not exist prior to measurement, then neither does the distance between them, meaning that the apparent space between two entangled particles located at opposite sides of the galaxy does not actually exist. What we see as space only emerges from the entanglement after someone makes a measurement.
So let me explain why the matrix. We talked about sort of things not being able to move faster than the speed of light. And I think the people that came up with the name of the matrix actually had something pretty good in mind there. Because what is a matrix? It's essentially something that relates something that's here with something that's completely somewhere else.
But what do we do with this new piece of information? How does knowing that the world emerges from entangled information help us in understanding what is simulating the world or why it is this way? As it turns out, an astonishing clue arises not in physics, but in cognitive science. Chapter 6. Entangled Consciousness. Giulio Tononi from the University of Wisconsin-Madison is one of the world's leading cognitive scientists, and the inventor of the most successful model of consciousness to date, Integrated Information Theory, or IIT. IIT arises from a simple realization about consciousness. Whatever other theories we have about the mind, the one thing everyone agrees about is what subjective experience of consciousness is like.
So, based on this, you can formulate a first working hypothesis, which is this, that, well, if that's fundamental about consciousness, then if you want to build a conscious system, or you want to ask whether any system is conscious, well, that system should have a huge repertoire of possible states. So whenever any one of those states occurs, it rules out tons of other, and therefore is very informative. And number two, those states must be part of the repertoire of a single entity.
Consciousness reduces to information in the form of percepts or ideas integrated together such that they behave as an indivisible whole. The green on a watermelon, for instance, is never seen separately from the information describing its round shape. These two bits are said to be integrated.
Consciousness is information. It's an information field. Okay? It's data.
And as it turns out, according to IIT, entangled information is necessarily integrated. As Giulio Tononi states in Consciousness is Integrated Information, a provisional manifesto, quantum entanglement and integrated information, to the extent that one cannot perturb two elements independently, they are informationally one. If true, this would mean that the entangled information that spacetime emerges from in the ADS mirror correspondence is in fact consciousness. But is there any way to experimentally verify that entangled quantum information is consciousness? The answer is yes. Though Tononi's model applies to information in general, and not just entangled information, it turns out that entangled information in the brain correlates directly to consciousness anyway. Quantum mind theories were once thought to be problematic due to the warm, wet environment of the brain that would supposedly prevent quantum states. However, with the advent of quantum biology, quantum effects have been found in warm, wet biological systems, including the brain. In 2011, Anirban Bandyopadhyay found topological qubits in microtubules. But perhaps more interestingly, the direct neural correlate of consciousness, gamma synchrony, was discovered to work by quantum entanglement. During anesthesia, the entanglement is disrupted and the consciousness is shut off. Restore the entanglement, however, and the patient becomes conscious again.
Patients under general anesthesia are unconscious, but if you do evoked potentials or measure EEG, their brains are quite active. We use evoked potentials all the time in spine surgery, and the brain is neurocomputing away in the absence of consciousness. What does disappear only is the gamma synchrony. So here we have gamma synchrony, and basically what's happening is that proteins in the front of the brain are oscillating coherently, and proteins in the back of the brain are oscillating coherently. And Walter Freeman and Giuseppe Vitiello, and in a separate paper, E. Roy John, concluded that normal neural processes shown here cannot account for this synchrony, and that some quantum effect must be at play in the brain to account for gamma synchrony.
Given that all of the other brain processes are still active during anesthesia, this evidence pinpoints consciousness to existing in gamma synchrony. Thus, conscious states are really states of entangled quantum information in the brain. However, if conscious states are entangled information states, and spacetime emerges from entangled information, then we arrive at an astonishing conclusion.
The very fabric of space and time is composed of more fundamental spaceless and timeless entities. I have a proposal. Those spaceless and timeless entities that they're looking for are in fact conscious agents. And the stable dynamics of those conscious agents actually leads to the bits of Minkowski space we need to piece together to get the unified theory we're looking for.
Consciousness is the only thing that is fundamental. Everything else is derived from consciousness, including this physical reality. Us, our bodies, our brains, whatever. We are all derived from consciousness. So consciousness is the fundamental reality. All else stems from that.
The mysterious source of the universe's simulation is uncovered. Physical spacetime is an information construct being generated by consciousness. Chapter 7. The Mind of God. This being the case, only one question remains. Is it being simulated by a single mind, or many? After all, we see different entangled systems throughout nature that appear separate. The answer is that entanglement, and thus information integration, may be relative to one's perspective. To demonstrate, it may be useful to examine the famous Wigner's friend thought experiment, a variation on the famed Schrodinger's cat thought experiment. But first, it would be helpful to look at Schrodinger's cat.
Let's say we put a cat and a vial of poison in a box. we add an atom of radioactive uranium and a Geiger counter. If the uranium decays, it sets off the Geiger counter, which then releases the poison and silently kills the cat. Before we open the box and look, we can't actually know whether the uranium has decayed or not, since radioactive decay is a probabilistic quantum event.
Here's the question. Is the cat dead or alive? Well, according to quantum mechanics, the cat is neither dead nor alive, but the sum of the two states. Well, at that point, you say, well, that's nonsense. That's preposterous. How can you be both dead and alive simultaneously?
Schrodinger's cat was supposed to show that nothing in this universe is certain until someone makes a measurement.
Before we open the box, the cat, the poison, and the radioactive isotope are all in superposition together and belong to the same quantum state. As such, they are entangled. When we open the box to observe the cat, we break the entanglement. But who is to say we are not in a quantum state along with the cat and the poison? What if we aren't even the ones doing the experiment? What if someone else observes the cat?
But another pioneer of quantum mechanics, Eugene Wigner, believed it could teach us something else about the working of the universe. That consciousness controls everything.
Wigner said, let's take it one step farther. If I, a human being, looks at the cat, I am conscious. Therefore, consciousness determines existence. At that point, Einstein went ballistic and said, what? You're saying that the fact that you are a conscious being determines the fact that the cat is alive? Answer is yes. And Wigner made one more step. And that is, how do I know I'm alive? You see, the cat and me, we're part of the same universe. If I don't know the cat is alive or dead, I could also be dead at the same time and not even know it. So who determines that I'm alive? Well, Wigner's friend looks at me, I look at the cat, and we exist.
From the reference point of someone outside the room where the experiment is being done, we are entangled along with the cat. But from our reference point, we are not. Thus, whether or not something is entangled becomes relative to one's frame of reference.
But then who looks at Wigner's friend? And there's an infinite chain of people looking at people, until finally you hit cosmic consciousness. Some consciousness that's ethereal, that envelops the universe, which looks at us and says, aha, the cat is alive.
So is there some reference frame in which the entire universe is entangled in a single conscious state? As it turns out, there is a way we can know for certain. If there is a reference frame in which the entire universe is entangled, then from that frame everything must share the same quantum state and be defined by the same wave function, the mathematical description physicists use to describe the quantum state. But is there a wave function for the entire universe? In 1967, a pair of physicists, John Archibald Wheeler and Bryce DeWitt, developed the Wheeler-DeWitt equation, which defined the wave function of the universe. In the process, they discovered that a universal wave function must have two curious properties. Firstly, it must have an energy value of exactly 0, and secondly, it must be time-independent or timeless. Given that these properties are unique to the Wheeler-DeWitt equation, they provide a way to test for the wave function of the universe. If time was found to emerge from entanglement, the time we experience would not be fundamental, but would have to emerge from a timeless quantum state, entangled by a single universal wave function. A universal wave function that would encode the conscious state of a single universal quantum mind, simulating the entire universe within it.
Is everything here created by God? Well, yes, if God's the larger consciousness system, yes. So you go through all, what are these attributes we call God? And you'll see that the larger consciousness system fits all those attributes like a glove.
But what do we do? Do we dare look? Do we dare use naked science to look directly into the face of God?
Marion, don't look at it. Shut your eyes, Marion. Don't look at it no matter what happens.
Well, in 2013, almost 50 years after it was proposed, this property was used to test the Wheeler-DeWitt equation directly. Once the experiment was carried out, time was discovered to emerge from entanglement. The Wheeler-DeWitt equation was proven true. Science had found that a universal wave function exists. a wave function entangling a single integrated information state within which the entire universe is simulated, the conscious state of an omnipotent, omniscient mind. Chapter 8, Epilogue. After the falsification of atheism, questions still remain. How does the scientific creation of the universe? What lies beyond Bredgen's other? How do our minds fit into all of this? What other surprises will we find along the way? Whatever lies ahead, one thing remains certain. The old lifeless notion of material atoms in an empty void is dead, replaced with the mystery and grandeur of a mental universe simulated within the mind of God.
If you like this video, subscribe and support me on Patreon. And don't forget to check out my novel, Alaris, The Lances of Light, on Amazon Kindle in the description below. You can find us on Facebook as well at Idealism and Science versus Atheism.